okay, now we are going to be moving to the actual part of our class. Until now, it was just discussion and it was just a basic introduction to the class. The first most important thing in our class is known as flux. Okay, the flux is defined as the rate of transport of a species per unit area in the direction normal to the transport. Okay, so if you look at here, you can have molar flux and mass flux. When we talk about flux, we are saying that rate of transport. So we are making rate of transport, it can be how much mole or how much kg is being transported per unit area. Okay, so that's why you have per meter squared, and how fast, because per area and rate here, right? Rate meaning that it will always involve time. Okay, so the unit for molar flux is going to be mole per meter squared second, and unit for mass flux is going to be kg, meter squared second. So depending on the problem, you might be asked to find the value of molar flux, or you have to find the value of mass flux. And these two values are interchangeable. You can just use the molecular weight to change from mole to kg or kg to mole. Okay, and then you can have two types of flux. One flux is due to the molecular diffusion. Okay, so we look at that after this in more details. And then you can have another flux due to the convective diffusion. So if you remember just now, I did mention that if your system is stationary, like just now we said that, you look at the YouTube video, you have water and then you have a drop of dye, it is diffusing, the high concentration is diffusing to low concentration. The one we call it molecular flux, because the only forces acting there is your concentration. There is no other external forces. But when you stir, for example, you put a stirrer, right? You put a stirrer, you are stirring it, so you are adding additional forces. You are adding a velocity to it. And when you adding velocity, so in order for you to find the flux, the total flux here, so it will be total flux is equal to molecular flux plus the convective flux. Okay, so this is the formula. So when we have the symbol of Na, this is it means that it is the total flux of component A, which is a combination of molecular flux, which is known as Ja, plus Xa again is your mass fraction, and this one, if it's Xa, we can know this is in liquid form, and N is the value of flux. And we can also convert this into this kind of equation, where Na is the total flux, Ja is your molecular flux, Ca is your concentration, and V is your volume. Okay, so the definition and the derivation of this equation, both of this equation, you can refer to the chapter of the textbook that I have uploaded into the e-learning. Okay, so first of all, okay, so this is how, if we were to represent, how does it look like in terms of molecular flux and the convective flux. Okay, so you combine this and then you'll get this value, this equation. Okay, so some definition: total flux, amount of a quantity passing through a unit area per unit time. Convective flux, amount of quantity passing through unit surface area per time that is carried by some reference velocity. So this is important here, because when we are talking about convective flux, there must always be a velocity term here. Diffusive flux, amount of quantity passing through a unit surface area part time due to the diffusion, right? Only diffusion. Okay, there is no velocity involved here. And it can also be the difference between the total flux and the convective flux, right? Because if you want to find the value of JA, just total flux minus the convective flux, you can find the value of JA, and then cannot be defined independently of the total and convective flux. Usually it will go together. Okay, but before we come to the total flux and how to find convective flux and diffusive flux, we'll be looking at it at one by one. So first of all, we'll be looking at diffusive flux. So diffusive flux is actually discovered by a person named Fick in 1855. Okay, he did some observation and found that during ordinary molecular diffusion, a component diffuses in the direction of decreasing concentration, meaning that here from high concentration to low concentration. That is the meaning of direction of decreasing concentration. The mass transfer rate is proportional to the normal area to the direction of mass transfer, and then the net mass transfer stops when the concentration, uniform concentration, is achieved, meaning that here when the system is already in equilibrium, when there is no more concentration gradient. Okay, so when there is no more concentration gradient, there will not be any molecular diffusion. And based on his observation, he came up with this law known as Fick's law. So if you remember, this is similar or analogous to our Fourier's law for conduction heat transfer, right? If I were to write it here, say Q is equal to negative Ka dt over dx. This is our Fourier's law, right? So if you look at here, instead of Q, we have J. J is known as our molecular diffusion flux, right? And then we have here negative. We also have negative here. So why do we have negative here? Because it is moving from high temperature to low temperature. In our diffusion, in Fick's law, we are saying that we have this negative here because it is moving from high concentration to low concentration. And then here we have a term of thermal conductivity, right? It depends on the material. If you have a copper, you have thermal conductivity copper. If you have insulation, you have thermal conductivity for insulation. Here we introduce a term called diffusion coefficient. Now, diffusion coefficient is also similar to thermal conductivity. It also depends on material. But the only difference is that if I were to write here DAB. So what does it mean here? We are saying that this is the diffusion coefficient of diffusion A into B. That's why we write A first and then B. Okay, A into B. So remember, when we define our mass transfer, we have to have a minimum of 2 components in our system. Then only diffusion can happen. If I were to find the value of JB, okay, if I want to find the value of JA, I write diffusion of A into B. But if I want to find the value of JB, I have to know the diffusion value of B into A. And then this is going to be DCB and DZ. Okay, so you must be able to identify and understand what is the difference between DAB and DBA. Okay, and then here, if you look at our Fourier's law, we have temperature difference. Why? Because we say that in heat transfer, it is based on the temperature. The amount of heat flux or heat loss is based on the temperature difference. When we are talking about diffusion, molecular diffusion to be specific, JA here, we are referring to the difference in concentration. How much concentration is changing. and this one is the distance. This one is also distance. So here it can be unit of meter, centimeter, feet, or whatever. So you can see here it is analogous to each other. Okay, so your job is to understand everything in this equation, each of these symbols and what they represent. Okay, so I've given the definition here. Okay, JA is what, DAB is what, CA is what, Z is what. Okay, now Fick's law is a little bit special because it can also be written in mass fraction, and it can also be written in weight fraction, and it can also be written in pressure, in terms of partial pressure. So from this original, so if I were to write it here, we are just looking at this equation. This is JA is equal to negative DAB dCA over dZ. Okay, so if you look at here, this CA value is our concentration value. Now we already discussed and we already saw how CA is related to XA, right? Because we know that XA is equal to CA over C, right? Concentration of A over total concentration. So since we know this relationship, we can actually change our term dCA here into dXA here, and we can get our Fick's law based on mole fraction. And then we can do the same thing and get the Fick's law in terms of mass fraction. Okay, so again, please go back and try to derive this. This one is number 1 in terms of mole fraction. This one is number 2 in terms of mass fraction. And if we are dealing with gases, if our system is gases, you can have in terms of partial fraction, mole fraction of gas, and you can also have it in terms of partial pressure. Okay, so this one is the third. So you must be able to actually change from this dCA term to get your dXA, dWA, and dYA. Yeah. How do you do that? You can use all this relationship that we discussed previously. Okay, so please go back and try to get these 3 equations. These are very important equations, and sometimes depending on what information is given and depending on what information you want to find, you must be able to actually change this original equation into equation number 1, number 2, or number 3. Okay, this is actually simple. You just have to know relation between mole fraction and concentration, mole fraction and molar concentration, mole fraction and mass fraction, and mass fraction and mass concentration. If you know that, you should be able to solve and to get all these 3 equations.